we welcome Emmanuel Dartois, who is going to talk about matter radiation interactions in the X-ray wavelength range in the laboratory.
So the title of the talk I will start with is less ambitious than the one that was given at the beginning, and I will start this presentation by a disclaimer. I should not be considered, and I will not be considered as an X-ray specialist, so it will be a kind of appetizer between some of the presentations about what I will touch lightly after by Elisa Constantini and Jean-Hugues Fillon. And maybe it will raise some questions for the roundtable afterwards. So before to start with, I will start with very simple things to put the context of the talk. I will mainly talk in this presentation about X-rays in the first part as an energetic radiation source that make evolve dust and gas in the interstellar medium, and then as a probe of the composition of this medium. Just to start with, I'd like to show this simple plot of the interstellar extinction, the cross section for the interstellar extinction. That has some interesting simple things to note, because generally it's mostly represented from the UV to the far infrared, and if you add the X-rays, you immediately see some features, and in particular the one related to the integral field units, spectroscopic units, that will be the main driver of this talk. If you go to the soft X-rays, then you note that the extinction cross-section at the carbon and oxygen KH in the X-rays is in the range in terms of extinction close to what is the UV VUV extinction. And then if you go to higher energy, then you will probe denser medium with the high energy of the XIFU at the same level, more or less, to the infrared. So as a source, X-rays are, all stars are X-ray emitters. And an important aspect of what I will discuss after is the emission varies with the age of the sources, and the younger the stars are, in general, the higher X-ray and flux they have with respect to what is observed, for example, in the sun. And this is one of the driver of the astrochemistry using X-rays, because one important aspect that will that is related to the range covered by Athena is the X-rays as a source, and in particular in young disks. This is just here a sketch of a model of the irradiation of a flaring circumstellar disk close to a young star. We can take as an example the TW Hydrae, which is a young X-ray, strongly X-ray emitter source. You have on the right here the spectrum that is emitted, but only in the X-ray range. This spectrum generally arises from the inner part of the source, where you have the accretion shock producing a strong X-ray and ultraviolet source. Importantly, in the models you see in the two upper plots, you see the field and how it penetrates into the disk. One important aspect is that the UV field is extremely intense, but at some point it will be screened from the outside, and then at some point the X-rays, the soft ones but also the hard ones, will penetrate deeper, and so you have a kind of stratification of the input of energy you can get into this kind of objects. from the VUV, then to the soft X-rays, the hard X-rays, and then you go back to secondary VUV and external cosmic rays irradiation. These are sources of evolution, and X-rays may in these cases be one of these sources. Here is represented another model, a previous model. The first one was in photons per square centimeter per second. Here it's put in another way in terms of deposited in energy in erg per square centimeter per second, with the same kind of stratification. And there have been some models looking at the effect of the X-rays and the UV and the combined effect of X-rays and UV on the chemistry occurring in this kind of disks. And one lesson from this kind of models is that in some cases, the one in the middle here, for some species like N2H+, the input of UV and then X-rays affects significantly the column density of this species as should be observed in the disk, whereas for some others it has quite not a lot of effect on the chemistry. So it's very important to know where to locate the impact of the X-rays in these cases. Another model, just to go through the literature, the X-rays from the source is a very strong and important source, but it is facing sometimes a very high amount of gas and dust, and so sometimes it's quite blocked already, and so the impact into the disk directly from the star is not that huge, but the location of where you find young stars sometimes occurs in young stellar associations, and so you can get the X-rays emitted by other stars, nearby stars, and so you can have a chemical impact coming from the background field of the surrounding stars. This is what was explored in this model, where you see here different radicals and ions in different models with different levels of background irradiation. And you see that in the inner part, you don't get a lot of difference because of the central source, but the background X-ray field can penetrate from the rear part of the disk and affect the chemistry. So important to constrain our laboratory with the laboratory experiments are all the processes that you will input in this kind of models. And one of them is the desorption of the ice mantles condensed on top on dust grains in the dense part of this kind of disks. There will be a talk by Jean-Hugues just after Elisa on this topic. I put only 1 or 2 slides here to show that they monitor experimentally the photodesorption yield of a given species condensed on top of grain as a function of X-ray energy here at about 500 eV. Then combining this to model spectra of X-ray sources, they can infer at different depths into the disk the rate and the efficiency of the desorption induced by X-ray when you re-put H2O in the gas phase. And if you look at this diagram at different densities, if you do this pair photon, basically what you see that at very high densities, only the hard X-ray penetrates. So you have a mean energy of 5 keV. So you will have an efficiency that is almost 2 orders of magnitude less than the one you get with the soft X-rays at higher energy. They measured this team has measured many other ICs. I just put here 2 plots that will be discussed after in more detail. So at the oxygen KH for other ICs, COIs and CH3OH ICs, but Jean-Hugues will detail this after. So there have been other teams working on the synchrotron X-ray ice, in this case photolysis. So not looking at the desorption itself, but looking at the modification of the ICs upon X-ray photolysis, in particular on complex organic molecules, here with a broadband irradiation up to 2 keV. Again, on synchrotron radiation, this is the Brazilian synchrotron. And looking at the effect for CH3CO, CH3 ice in this case of the production and destruction of species, and determining some cross section that can be put into models for this for the evolution of these ices in case they are subject to X-ray. But these are really broadband experiments, so it's a complex interpretation. There have been other synchrotron X-ray experiments, also combining desorption and photolysis by X-rays. Experiments using layered ices. So the idea here is to have two different ice mixtures and to have a look at what's going out from the ice when you expose it to X-rays. So you have both the modification of the bulk by the photolysis by X-rays of the system, and also as you have a different mixture, you can to some extent try to separate something that would come from the bottom layer and the upper layer. And in this specific experiment, with a topping of CO and CH3OH ice, they saw no CH3OH going out, and they saw only the products of the destruction of this species desorbing, but they also saw some molecules and used deuterated molecules to see that some of the ones from the bottom were coming out after some times of irradiation. So they formed combs but do not desorb them easily, and they also form the products because of the X-ray irradiation that went out from the bottom layer. There have been, continuing on the solids that may be of interest, there have been some experiments on the organics X-ray destruction, not related to the same field exactly as the one I was discussing before, but for example, there have been 500 EV experiments on poly-HCN-like analogs, so some like to call them tholins. Organic system with carbon, nitrogen, and hydrogen. And you see in these experiments performed again on synchrotron that after the first irradiation step, you almost have everything that has disappeared that concern the CH, CN, and you get a huge absorption linked to the carbon backbone. But these experiments were performed at very high fluxes, 310 to the 26 EV per cubic centimeter. So it's about 410 to the 5 EV per cubic nanometer. So it's really huge fluxes. And so to affect organics, you really need to have, in this case, huge fluxes. There have been more recent experiments on another kind of organic without nitrogen, polyaromatic organic, and they looked at the infrared 3.4 micron absorption band, which is related to methyl and methylene bands. After a dose of 510 to 26 EV per square centimeter, they could destroy 80% of the band. So it means 510 to the 20 photon per square centimeter. Just as a reminder, 1 million year is about 10 to the 13 seconds, so it means 10 to the 7 photons, so 10 to the 7 keV photons per square centimeter. So it's still a lot for a disk. There also have been some irradiation of silicates with soft X-rays, again with broadband experiments here on a Taiwanese synchrotron beamline. And after a few 10 to the 21 EV per square centimeter deposited, they could show that there is a change in the band monitored by infrared here of the SiO bond, which is attributed to the amorphization of the silicate in this case. So another mechanism, additional mechanism to amorphize silicate in space with X-ray photons, but still quite high fluxes. silicate irradiation had been performed already with harder X-rays here at 30 keV. In this time, it's again a synchrotron. It's the Grenoble ESRF1. You have a diffraction cliché here showing that in fact nothing changed almost between starting either with an amorphous or crystalline silicate after 10 to the 27 EV per square centimeter. So this there have been only one of the sample which was really modified during these experiments. So it means that there is really, for this kind of energies, the need for extreme fluxes, and in terms of the region that may be affected, it mainly means mostly means region that would be directly facing the star, and not the one that are already to some extent further away. As we will see in the presentation after by Elisa Costantini, the X-rays can also be used as a probe of the interstellar medium composition. Here is an article they produced looking at the interstellar medium absorption already at the magnesium and silicon K age. And by comparison with analogs, again measured on synchrotron beamlines, they could deduce in this line of sight that the dominant form of silicates is an amorphous olivine, for which you have a sketch on the right side of the slide. There will be more detail in the presentation. I won't go into more details of that. Just to mention, from the lab point of view, there are also many experiments on extraterrestrial samples that are using X-rays. So I present you just two slides on an example I know well here on micrometeorites. These micrometeorites or meteorites are generally harbor an intimate mix of mineral and organic matter mixing, and some of them can be looked as good analogs or something we would like to compare to the spectra that could be recorded by Athena. Here are thin slices made by a focused ion beam of these micrometeorites, and they are also analyzed by X-ray, generally with techniques like STIX and XANES, to understand the speciation. So you have the spectra in absorption you expect at the CKH and nitrogen KH of this of these analogs. Just to say that there is also an ample literature on this kind of thing that could be used also to have as a reference to compare to some of the spectra of the ISM that may arise from the Athena spectra. Just to mention it, also in the X-ray extinction modeling, for the discussion, of course, what was presented before was done with bulk material or natural samples, the extraterrestrial one. But there is also a need to be sure from the modeling that we are able to interpret the dust size distribution and its influence even in the X-ray domain. So generally, the X-ray domain is considered as exempt of strong scattering, but it is not fully the case in some cases. And this article was discussing this, looking at what would give the X-ray spectrum of the interstellar medium for the best model that reproduce, one of the models that reproduce the interstellar extinction in all the other range of wavelengths. What is to be kept from this discussion is the fact that from the absolute values of the extinction, scattering of X-ray should be taken into account for a good modeling of the interstellar medium. And also in some cases, the grain morphology also, if you take spheres or spheroids, for some of the edges, this will have an importance on the detail for the mineralogical composition extracted. For example, here at the oxygen KH and iron KH. Even the shape of the grain may have an influence of what is extracted from the sample. Whereas, for example, for the K iron, it's only an absolute value, and so the shape is not really modified. But this is something that may be interesting to take into account in the future analysis of these of the future data from the XIFU. I will shortly end, and before that, other experiments. In this case, in the gas phase for big systems. There are also synchrotron experiments, again here on the Brazilian one, I guess, on the X-ray photodestruction and photoionization efficiencies for big systems, in this case naphthalene. Irradiated here with soft X-rays at 275 eV and then at 2.5 keV. And here you have the mass spectrum recorded upon irradiation. So you have the ionization of naphthalene, and you see a lot of fragments here that are due to the photodestruction of naphthalene. But you see also a large peak here at half the main one, which is simply the fact that you are seeing the doubly ionized species. So you have a competing exit route between the photodestruction and the photoionization of this system, and this will change with energy. You see here that you have more photoionization than photodestruction, and at much higher energy, you have more destruction in that case. These are normalized, so it's not the cross section. The cross section is more efficient for this energy than this one. But once you make this interaction, then the photo destruction is higher here. This has been applied as a half-life estimate in this case to region near active galactic nuclei in first estimates on the survival time that would have naphthalene in this kind of environments. Another experiment of the, let's say, of the same kind, this kind with biphenyl, again with PEPICO experiments. So again, time of flight experiments looking at the fragments, and if you look into the very detail of each peak, you will see all the possible fragments as well as the double ionization of some of the fragments. And again, this was applied in this case to estimate the half-life of this kind of species. In this case, it was applied to a protoplanetary nebulae environment. So I will end this presentation here. As I said, it's just a flavor of many of the experiments that are done to interpret the consequence of the sources, of the X-ray sources that will be measured with the XIFU and the absorption in the X-rays of the interstellar medium. So the keywords are, you've seen many things about disk associated with young objects. For the components, experiments on the volatiles, refractories, and gas with X-rays, the absorption of the ISM, and I put really naive statements that what should be done for better knowledge about that is to support the experiment, and many of the one I have shown here are coupled to synchrotron beamlines because X-rays are better handled and manipulated on this kind of lines, plus all the subsets you need to couple to these beam lines. So the small experiment reactors, analog production in some cases. And last but not least, there is a need to implement this X-ray experiment result explicitly in models to really understand where their impact is the highest. The good example is the one of the disk I was saying. So you have a kind of stratification, and so you really need to progressively implement this into astrochemical models to see where they have a role to play, and specifically. And thank you for your attention.
Thank you very much. So now, if there are questions, okay. Okay, Jérôme, he asked, so in your layered ices, why H2 and HCN are below CO? Is it an experimental constraint or is it astrophysically motivated?
Sorry, I only had half of the question.
Okay. Okay.
Jérôme.
Can you hear me? Oh, no?
I can ask my question maybe.
Well,
The question is why is H2O NH3 C4H CH4 below CO? Is it a constraint of the experience or is it astrophysically motivated?
We can say it's astrophysically motivated in the sense that in dense cloud you see this kind of stratification in the dense region. So if you go to very dense regions, you have region where you observe pure CO on top of H2 if you look at the ratio of CO to H2 as a function of depth. And so I guess that in this case, they put CH2H because CH2H is sometimes advocated to be produced only by hydrogen reaction of CO. Well, we can agree or disagree on that, but I guess that's the motivation of this layering. After that, from the fundamental point of view, you could also change the mixture, but the idea here was also to have two layers to see if you can get some information from the layers below the CO1.
In fact, I had another question that has nothing to do. 15 years ago, we were speaking a lot about XDR and their impact in chemistry, and but we don't hear it so much today about. So, do you have a feeling about whether XDR are important compared to PDR in interstellar medium, or?
I think that it's outside of my expertise for the moment, so that's mostly that. But yes, it would be important if you have really strong X-ray sources. But as I said, it's really important to have the global view on the system, because generally strong X-ray emitters are also strong VUV emitters. So it would really depend on the density, shape, and there are also many subtle things that should be taken into account in models. The scattering of the UV field is much easier than the scattering of the X-ray field. So the secondary penetration. So this has to be set finely into models. All these aspects are important. So we have to measure all the wavelength range, but then to know where it acts effectively, we really need to implement these details. It's a lot of work.
okay, I also had a question, but can you hear me or not?
Yes.
Yes. I was wondering, it's about the impact of X-rays on carbon matter. You showed the example of naphthalene, so it loses its H or its well, yes, there is this cascade. And when you showed the example of biphenylene, it's funny because the CH the hydrogen remains. So I was wondering why, because it's really strange as the paths are not similar. I mean, losing all the H and.
No, I guess that in the first articles they just mentioned the fact that it was the C3 peak with hydrogen, okay. C2 peaks with hydrogen. It's just a figure simplification, I guess.
Okay.
You will have also all this inside the peak as you see it for biphenyl. Maybe the biggest difference with biphenyl is that you do not see a lot of biphenyl doubly ionized. You see more the fragment of biphenyl doubly ionized in this case.
Okay. There are no more questions, no? So thank you very much, Emmanuel.